Okay, this video looks at Objective 3 from ILM 302B, operation of three-phase induction motors, and covers induction motor characteristics. When you look at Objective 3, Figure 3 is the same figure that we have on the screen here, and it's worth going through just to explain to you what is happening with the overall three-phase motor as we're adding load to it. And one thing to be sure you're clear about when you're looking at this graph is we've talked about, at the start of this ILM, we talked about what happens in the rotor of a three-phase induction motor as load is added to it. And there's a bunch of parameters that happen to the rotor itself when we add load to it, and it helps us to understand what's happening within the motor that causes the rotor to turn and causes it to slow down when load is added to it, those kinds of things. But this chart here is talking about the overall motor. What is happening overall, rotor and stator, in that motor as we're adding load to it. And we can start with rotor speed. And that's one of the best things to start with whenever we think about a three-phase motor. Whenever we add load to a three-phase motor, it's going to slow down. The next thing we can look at is as soon as we're adding load to this motor, if we have basically no load at this point in our graph and then are slowly adding load, and so the motor has to provide more power to turn that load. So as the load is added to our motor, we'll see that the slip goes up, which means that the rotor is slowing down. As we add load to the motor, the rotor is slipping further behind the rotating magnetic field produced by the stator, which always turns at synchronous speed. As we add load to the motor, the output torque increases for sure. As load is added to the motor and the rotor slows down, and because the rotor is slowing down, more current is produced in the rotor from the magnetic field cutting across the rotor bars more, and that extra current provides torque to turn that load at a slower speed. So up to breakdown torque, you bet, our output torque increases as we add load to the motor. And as we add load to the motor and the rotor slows down and we have increased current produced in the rotor, that current is reflected back onto the stator. We always say that a motor is like a rotating transformer, and if the power is increasing on the rotor, the power output is increasing on the rotor, we can think of that as the output of the transformer, and power output equals power input. So as the current is increasing in the rotor, that current is reflected in the stator, and the stator current will increase as well. You can see in our graph that as load is added to the motor and our torque and current increase in our motor, that our power factor also, as we add load, increases up to a set point. In our rotor, when we look at just our rotor chart, the rotor's best power factor is at no load. It's basically where the rotor speed is closest to synchronous speed. That's the best power factor in the rotor. But when we look at the rotor and stator combined, the way power factor works in the overall motor is that it slowly increases as our load increases up to a set value. And this is another good place to point out that one thing you should always be asking yourself when we talk about power factor, efficiency, how a motor works best. If we ever ask ourselves the question, when is a motor going to be working at its very best? It is designed to operate with all factors at their very best at rated horsepower of that motor. So when that motor, in this example we have a 10 horsepower motor, when that motor is loaded down so that it is at 10 horsepower, if we had a watt meter an output meter on it and saw that we were at 10 horsepower, approximately 7,500 watts. When we're at that output horsepower, this RPM, this is full load RPM, we would also be at full load current. That is when the motor is designed to operate it at its best. And when you look at this chart and see for this 10 horsepower motor, that is where our efficiency is basically the best. Our power factor is absolutely the best at that point. Speed, current, torque have all become, we're actually at rated values for that motor at 10 horsepower. But that is where the motor is designed to operate at its very best. It does not work as efficiently at half load. It definitely does not work as efficiently at 150% load. It's designed to operate at its very best at rated load or nameplate horsepower. So of course, as the load is added to the motor and we go from a low amount of power that we need to turn our load up to the rated horsepower of the motor, the efficiency is going to increase of that motor as well, and it should be at its best efficiency at rated horsepower. And then get worse. Power factor, efficiency, both get worse as you go overload for that motor. And this chart here is basically from page 19 of Objective 3. And again, just talks about what's happening with our motor as we start it from a dead stop and start it and bring it up to rated speed. And generally what we will always see with a squirrel cage motor is when we first start the motor, the current that motor draws will be 6 to 7 times its rated current. We are at blocked rotor values for the motor where the rotor has not started turning at all, and it draws a high stator current because the rotor current is the highest it will ever be as well. And our torque is often not the maximum torque we can get out of the motor, but it's generally 2 or 3 times the rated torque of the motor. So we get pretty high torque at startup for our load as well. And then as the motor speeds up, our stator current starts to drop off as the rotor turns quicker and quicker. Our starting torque will actually come up to a maximum value when R and XL are the same values. So generally as the motor starts, the XL is generally a lot higher value than the R in a typical squirrel cage motor. As that motor speeds up, the XL drops off until it gets to a point where XL and R are the same value. At that point, we have maximum or breakdown torque produced in our motor. From there, it generally drops off as we speed up to between no load and full load speed, depending on the load. And at no load, of course, our rotor will be turning very close to synchronous speed. If the synchronous speed of a motor was 1800 RPM at no load, that rotor will be turning 1780, 1790 RPM, so it turns very close to synchronous speed. As we add load to a squirrel cage motor, the very first thing that happens is the rotor slows down. But an interesting thing to note about how the torque works too is when we add load to our motor and the rotor slows down a bit, it provides a lot more torque as we slow down just a little bit. This curve is going up very quickly towards maximum torque. So we only need to slow down a little bit to provide a bunch more torque. As we add load, if we add some more load, it'll just slow down a little bit more to provide a bunch more torque again. And we'll get to a point, of course, where we're at rated torque for the motor, roughly here in this chart. And the thing to keep in mind, of course, is most motors are designed to provide more torque than you use at full load, so that if we accidentally overload the motor a bit, it will continue to work for us. And if we get past the full load for this motor and put more load than it's rated for on, it will just continue to slow down and produce more torque. Now it's also drawing more than rated current that would draw at full load. And so eventually, if we leave it overloaded, the extra current it's drawing should cause the overloads to trip. But we should keep in mind too that if we add a sudden large load to the motor and we happen to get to maximum torque, if we were to load that motor right to maximum torque and then actually exceed that a little bit, as soon as we exceed maximum torque, we slow down some more, but we don't get more torque, we get less torque, and that motor will come to a dead stop and become blocked rotor. So that's just a couple things to notice from this chart that they show you on page 19. The one other thing to point out from this objective is on page 21. I don't have it on a slide to show you, but on page 21 there are a number of rotor quantities that they talk about that relate back to basically the rotor chart, but it's worth looking at the 2, 4, 6, 8, about 11 bullets that are in the middle of page 21 as a review of what happens with our rotor in our motor when we add load to it. That pretty much explains objective 3. Hopefully that helps you understand the motor characteristics and how they can be slightly different overall for a motor than they are for the rotor itself. That's it for now.